Today we're going to take a look at right triangle trig, and we're going to see another way that we can define the function sine theta, cosine theta, and tangent of theta. Now the way we defined these functions in the past is we took an angle theta in standard position, and we said, well, wherever this angle meets the unit circle, we get the point x comma y, and sine of theta is just the y coordinate of that point, cosine of theta is the x coordinate, and tangent of theta is y divided by x. Now what we're going to do is we're going to take that point, we're going to drop a line straight down to the x-axis. When we do that, we form a right triangle. And notice the bottom side of our right triangle is the same as the length of our x-coordinate. The other leg of our right triangle is the y-coordinate, and the hypotenuse of our right triangle has length 1, because after all, this is the unit circle. And now what we can do is we can kind of redefine sine, cosine, and tangent. Notice y here, that's really the same as y divided by 1. That's the same as y. I can rewrite x as x divided by 1. And now let's rename the sides of our right triangle. So instead of using x, y, and 1, we can call y here OPP for opposite, because this side is opposite from our angle theta. The side x is adjacent to our angle, so we're going to call that ADJ. And the hypotenuse 1, let's call that HYP for hypotenuse. And now if we look at these three trig ratios, I can rename them. Y over 1, well, that's really the same as opposite over hypotenuse. Similarly, x over 1 is the same as adjacent over hypotenuse. And y divided by x, well, that's opposite over adjacent. And so we can define sine, cosine, and tangent in terms of these ratios instead. And just a little mnemonic here, you may have seen this before, SOHCAHTOA. This is just a way of remembering these definitions. It basically says that sine is equal to opposite over hypotenuse, cosine is equal to adjacent over hypotenuse, and tangent is equal to opposite over adjacent. Okay, now let's take a look at this example. So we have a right triangle, and our first job is to find side B. Notice we're given the leg A, we're given the hypotenuse C. We're also labeled this angle up here alpha. Notice that this angle is opposite from side A. So A here is our opposite side from alpha. C here, of course, is our hypotenuse. B is going to be our adjacent side. And our first job is to find the length of side B. And the way we're going to do this is using the Pythagorean theorem. So remember, the Pythagorean theorem says that for any right triangle, a squared plus b squared is equal to c squared, where of course a and b are the legs of our triangle and c is the hypotenuse. And if we plug in our numbers, what we'll have is, let's see, a is 7, so 7 squared plus b squared is equal to c squared, which is 8 squared. And if we solve this, let's see, we'll have 49 plus b squared is equal to 64. If I subtract 49 from both sides, we'll end up with b squared is equal to 64 minus 49, which is, what is this, 15? And then we'll take the square root of both sides. So we'll end up with b is equal to the square root of 15. Now, technically, when we take the square root of both sides, we get plus or minus 15. But since b here is the length of a side, it's understood to be positive. So this is our value for b, square root of 15. Okay, now let's find the trig ratio. So we're going to find sine of alpha, cosine alpha, tangent of alpha. And we're going to use these new definitions that we came up with. So sine of alpha is opposite over hypotenuse, which for our triangle is going to be 7 divided by 8. Cosine of alpha is going to be adjacent over hypotenuse, which for our triangle is square root of 15 divided by 8. And finally, tangent of alpha is going to be opposite over adjacent, which is going to give us, let's see, the opposite side is 7 divided by the adjacent side, square root of 15, which technically this isn't simplified because I have a radical in the denominator. So let's just rationalize the denominator. I'm going to multiply top and bottom by square root of 15. And when we do this, we'll multiply straight across. We'll end up with 7 square root of 15 divided by, in the bottom, square root of 15 times square root of 15 is 15. And there would be our simplified answer. Cool, so we found all three of these trig ratios. And now the last thing we're going to do is we're going to find alpha to the nearest tenth of a degree. And the way we're going to do that is we're going to use one of these equations up here in part B. And we could actually use any of these three trig ratios. I'm going to choose to use sine just so I don't have to deal with the square root, but really any of these three would work. Okay, so what we have is sine of alpha is equal to 7/8. And what we want to do is solve for alpha. And we can do that by maybe just taking sine inverse of both sides. Or if you want to think of just translating this into an inverse function or an inverse equation, this is the same as saying alpha is equal to sine inverse of 7/8. And now at this point we can plug this into a calculator. And you want to make sure that your calculator is in degree mode, right? Because notice we're asked to find alpha to the nearest tenth of a degree, so we should be in degree mode. And a tenth of a degree, that just means one decimal place. All right, so sine inverse of 7 divided by 8, rounded to one decimal place, would be 61.0 degrees.